There is a multitude of cases where the database system needs to sort data, and often the data does not fit into main memory as a whole, but still it needs to be sorted. And the algorithm to accomplish this is called external sort, which we will explain now. So you have like a huge file on disk, and this does not fit into memory. So what you have in memory is some space available, some space of, we will call it later, NB blocks. And now what we do in order to sort the file is to read as much as we fit into this buffer space. And then we sort this, that we just read into the memory, and we write it to disk in a sorted fashion. Then again we go and read more blocks from the file from disk. We sort them in memory, and we again write them to disk. These files, these sorted files, we also call runs. So we continue, we read from disk as much as we can, and then we sort it in memory, we write it in a sorted file on disk, and so on and so forth, right? So now we have, in this example, let's say this is it, the file is done, and we have here 4 sorted runs on disk. What we then do, of course we are not done yet because these files are individually sorted, but not globally sorted, so we cannot just append them to each other, we have to merge them. And how now external sort proceeds is to take, let's say in this example, 2 of these runs, and is merging these runs into a longer merged run. So like this. And we do this for the other 2 as well. And we get also here like a sorted longer run based on the run numbers 3 and 4. And now guess what's happening? Well, we are still not done because these blue runs are not globally sorted, they're just individually sorted within these runs. So we take them and also merge them into a longer run, and this is the final run, and we are done. Now the question is, how do we merge? Because merging can also not just load the runs into memory, so you cannot just go and load these runs into memory because they're too big, right? If you're looking at this initial file and it was too big to fit in memory, together these runs are the same size because we're always talking about the same data. And these 2 runs here have the same size as the big initial file. And even this last run obviously has the same size as the initial file because, well, it's the same data, right? It's just sorted. And the question is, or the trick is, to see how these runs are merged. And again, since we have some available memory, available buffer in memory, we can only piecewise read blocks from these runs in order to merge these runs into this run here, right? Now in this example, as we see, this is a small example, we have 4 runs after the first creation of runs, where we take the initial file and we step by step create these runs. So we have 4 of them. And here in this case, we take 2 runs and merge them into a new run, like a larger run, and here as well. So now we have 2 runs and finally 1 run. In this case, this is a 2-way merge. In general, this depends on the number of available blocks in the buffer. If it's like a 2-way merge, or like an 8-way merge, or a 16-way merge, or like a 25-way merge. So this depends on this parameter that describes how much space we have in memory. So a bit more concrete example with numbers. Here you see the input file. Here in the middle you see the buffer, which has a size of 4. So we can fit 4 blocks of data into the buffer. These here are the individual blocks. In the first block, which is marked here, there are 2 numbers in, 3 and 4. Here there are 6 and 2, and so on. So what we now do, we load the first 4 blocks into our buffer, We can do this because the buffer has a size of 4. And then we merge these numbers, or these we sort these numbers, and then we create one output run based on what is currently in memory, which is this, right? So we get a block with 2 and 3, a block with 4 and 4, and you see that this file now, this first run, this one file, the data inside the file is sorted. But we're not done yet, because we still have to read more from the file, from the unsorted file. And here we read 3 more blocks, the blocks that contain 5, 6, and 3, 1, and 2. Same thing happens, we load them to the buffer, we sort them, and we spill them to disk in a sorted way, and this gives us our run 2. So you see that these runs are individually sorted, but we cannot just put them together in one file and we are done, because globally there's no sorting order. So we have to merge them, and intuitively we would go and read one block from here, one block from here, and then we merge the numbers. So it will give us 1, 2, 2, 3, and so on. And then we continue, and we would go block by block over these files and create a merged version of these 2 runs, which is basically then a larger file. And in this case, we would be even done, because this is already the end of our algorithm. But in general, if you have many, many runs, then you have multiple of these merge phases where the runs are merged, and they're merged into longer runs until you're done. So how many of these runs do we have? Let's assume we denote with n the size of the file in blocks, and the available size in memory that is used for sorting, this is like the buffer size, again expressed in number of blocks, we call NB, as previously already introduced. And now we can specify the number of runs. This is the number of these little files after the first processing of the unsorted file, where every run has a certain size and is internally sorted already, right? These were these 4 little runs in our tiny example in the beginning, right? So these initial runs. How many do we have? Well, we have n blocks in the big file. So we want to sort, and we can load always nb blocks in memory to sort. And well, so we have n divided by nb runs initially. And this is, of course, the ceiling function here, right? It rounds it up. So an example, we have 1024 blocks in our big file, and we have NB, so the buffer size is 5 blocks. So in total we have 205 runs that we create. How big is each run? Each of these initial runs is 5 blocks big. Only the last one, because the division is not like going off perfectly, so we make use of the seal. So the last block is a bit smaller, it's 4 blocks only. So if we have these 205 blocks now, or these 205 runs, these are 205 files on hard disk. And now, after we created these runs, the merge phase can start. Yeah. So sorting phase, this is what we did already. So we have these many files on disk, these run files, and now we have to merge. And in the previous example, this tiny example, we had 4 runs. Now we can even make 5, 6, 7, 8, and now we can, let's say, take 2 each. So we have then 4 longer runs, and then we can take these 2, and then we have even longer runs, and then in the final step we have a long run, which is the size of the initial file, and we are done. In this case here, again, it's a 2-way merge, because we always take 2 of these runs to merge. We do that here and here and here and here. We always take 2. Here as well. It's always a two-way merge, and also here, of course, in the end. In general, it doesn't have to be a two-way merge, because we can take also more of these runs together. And how many of these runs can we take together? Well, if you're looking how the merge works, merging is done by reading from every run one block. And then you can merge, right? So if you have NB space available in the memory buffer, we can read one block from NB minus 1 of these runs, right? NB minus 1, Y minus 1, because one block needs to be reserved to create the output blocks that will be written to disk in the output file after they merged. So we can have NB minus 1 of these runs can be merged in one step. And again, this creates longer runs. And if you're now wondering what is the number of merge phases we have, because we don't have only one merge phase, as we have seen already here in the two-way merge example. So how many do we have in general? Well, we have the number of runs, NR, and the number of merge phases is simply the logarithm of NR, but not to the base of 2, like it would be for the two-way merge, but here the base of the logarithm is NB minus 1, because we can merge NB minus 1 of these sorted runs into a longer run at once. Another illustration, we have files on hard disk. These files are our runs that we created in the initial sorting phase. And now we can read from every of these runs, or from NB minus 1 to be precise, from NB minus 1 of these runs, we can read one block. Here's one block for the output. So in total, the buffer is full with NB blocks. And if this output block is full, we append it to a file, our output file, which is in the end, what the output file is the merge of all the runs that we can consume at once. So NB minus 1 runs we can consume at once. So the file contains NB minus 1 runs. And if we have, of course, many runs here, and we can consume only, or we can merge only NB minus 1 of them, in the end, then we have a set of files which corresponds to our new runs. Only in the last step, of course, we have only one of these files after the merge, and then we are done. So remember, it's a NB minus 1 merge because of the buffer we have available. So some example with numbers. So we have a buffer of size 5, we say, and we have a file that we want to sort, and this is 108 blocks large. So if we have in the first initial sorting these parameters, then we end up with 22 runs, right? And now, since we have a 5 size buffer, how many of these runs can we merge in one shot? 5 minus 1, right? NB minus 1. This is 4. So the phase 1, the merge phase 1, creates by a 4-way merge 6 sorted runs, which are of course larger than the initial runs. How large are they? Well, the buffer is size 5, so the very initial, the 22 runs, are of size 5. Here we are merging 4 runs at once. So the runs that come out of the phase 1, the pass 1 of this merge phase, there are 6 runs, and each run is 20 blocks large, right? Because every of these is 5 blocks large, and we merge 4 of them. 4 times 5 is 20. Only the last run is only 8 blocks large. So now we have these 6 sorted runs. They're still not done. We have to still merge them. And then we again apply this formula because when we have 6 runs and we do a 4-way merge, then we end up with 2 sorted runs. These runs are again not equally sized because of the mathematics behind that, right? It doesn't match up always, like a nice example where it's 16, 32 and so on. Anyway, so the first run that comes out here is size 80 and one run has size 28. And in the last merge phase, we merge these 2 runs and we're done. That's the end of the algorithm. So you see, it's all only, although it might look complicated because of all these equations and multiple runs, but in the end it's only, the only thing you have to really remember in order to visualize how the algorithm works is that you have a buffer available. And what do you do if you have this big file? You can only read chunks of this NB size. You sort them, and this creates small sorted runs. And you want to merge them. How many can you read at once? NB minus 1, right? And then, well, you just have to remember, then this is like the logarithm as the base, and this specifies then the number of merge phases you have. So in principle, it's not a very complicated algorithm. So some sample numbers. We have a file of n blocks, for instance, 100 blocks, or a million blocks, or billion blocks here, so quite large in the end. And here's our parameter NB, number of buffer pages we have available. And you see, well, that's a tiny number, right? I mean, this is not realistic to assume we have only 3 blocks available, but even then, you see that the number of merge phases is 7 here for 100 blocks. But again, this file is very small, this buffer is very small. Let's go to a bit more realistic numbers. Let's say you have 1 million blocks in the file initially, and you assume that you have 257 buffer space available, so blocks in buffer available, and then the math is easy. You just say 257 minus 1 because you have this 1 for the output block, and look what's happening then if you put in the numbers into the equation. The equation tells you there are 3 merge phases only, so you can sort a 1 million block large file with 257 blocks in buffer in memory space available, and you have only 3 merge phases. And if you go now, and this is like a nice behavior of the logarithm, you're going now to a file which is 1 billion big, you have only an increase of 1 additional merge phase, and then you can also handle this huge file, right? And this is like the cool thing about the external sort. With small available memory, you can accomplish sorting huge files. One thing to remember when we talk about, let's say, 10 here, so 10 merge phases, if you have the initial file, and this is size n, and then you're sorting it into these small runs, and there are of course many of them, right? If the file is big and the buffer is small, these together are also n big, right? They are small individually and sorted, everything's nice, but in total these are also size n altogether, right? And if you're merging them into larger ones, and of course you have less than in the second phase, let's say like this, doesn't matter so precisely, so the size of all together is again n, right? And then you're merging them again to larger ones, and again, this is n blocks. And finally, the output file, well, it's also n blocks. It has to be n, because the input is n, so the output should also be n. So every time you're doing these merge phases, you have to read number of blocks, which is correspond to the initial number of blocks of the file, right? So it's, of course, still, also this looks good in small numbers. You still have to do some work in order, to get the job done. And just to, I want to emphasize this because sometimes you say it's a big file initially, but these small files are in union always the same size as the initial file. Just remember that. So there's one extension to external sort, which is called blocked IO external sort. So what is this doing? It's a bit confusing, I have to admit, but this is named like this in literature. So we anyway talk about blocked I/O, like because we have a block storage device. But here, and anyway, we talked also before, always about blocks and pages, right? So we have also seen when we talked about hard disks that it's kind of expensive to read only one block from disk, from a file. But sequential access can harness, let's say, transfer rate of 100 megabytes or 200 megabytes per second. So it's much cheaper to read a whole sequence of these, right? So what the idea is behind blocked I/O in this external sort is to read entire chunks of blocks from runs instead of having only one block after each block for a specific run, right? So if you have now, again, so you have 4 runs, and you say NB minus 1 is 4, so you can read one block, 1 block, 1 block, 1 block, 4 blocks. But instead of this, you can also say, well, anyway, we already go to this file here and have to read, why don't we read 2 blocks? And here as well, 2 blocks. This will also fill up our buffer. So, and as you notice in this illustration, in this case, we cannot merge 4 runs at the same time, but only 2, right? But because we are reading more, the access to these 4 blocks is quicker than reading 4 blocks from different files. Now we read 2 blocks from 2 files. The downside here is, of course, that you need to have more merge phases, because as you can see, it's not a 4-way merge anymore. It's only a 2-way merge. Yeah, because the number of runs you can merge in one step is 2 and not 4, right? So the idea of this extension is to accelerate reading larger chunks from the runs at the cost of getting the space or the arity of this n-way merge down. So if you want to give it a different name, or let's say to get the problem a bit away of talking about blocks and blocks, this should also be called better like chunked I/O or something like this. Because anyway, we always talk about blocks, but here we talk about blocks of blocks, so multiple blocks sequentially, right? But this is only the name from literature, but perhaps it would be better to call that chunked I/O, because you're reading chunks, sequential chunks, to benefit from this fast sequential read compared to reading only the single blocks. Yeah. So now how many of these blocks do we read together? We read B blocks. So B blocks in one chunk we read from each run. And this means that we have this many runs we can merge in one phase, in one step. Yeah. So if we have NB is 10, we have seen previously that we have NB minus 1. So 9 runs can be merged in the traditional external sort, where we have 1 block per run as input and 1 block for the output. Now if we read 2 blocks from the input runs and have 2 blocks for the output, then we have 4 runs that can be merged at once. Yeah? And since we have less runs that can be merged, as I said already on the previous slide, the number of required phases grows, but the benefit is, the advantage is, that you have a lower cost for the block accesses. Yeah? And this is not really a problem here, the number of required phases, because as you have seen, this we went from 1 million to 1 billion and had only one more phase for 257 blocks in the buffer in this one table before. So if we have a little bit more available memory, even with blocked I/O, with some reasonable parameter b, we can still sort very large files in a few phases and benefit from the better performance because of the sequential reads of multiple blocks at once. So now the numbers changed a bit, of course, or the equations changed a bit. So we have now in the first phase still n divided by nb runs. That's the same as for the traditional external sort. But now we have not nb minus 1 runs that can be merged together at one point, but we have nb divided by b floor minus 1 runs that can be merged together. So this here is different. It's smaller than in the initial external sort. So if we look at the number of required phases, here this f matters then. So it's different than in the previous one. So this is of course causing that we have more of these merge phases, right? But again, the idea here should be clear why we introduced blocked I/O. Well, a lot of talking about sorting, and one application we have seen already earlier, sort merge join, right? If the data is not sorted yet, then we have to sort it first, and database tables can be pretty big, so we cannot just load them in memory and apply some in-memory sort algorithm. So this is like the first application. There are plenty more. For instance, if you want to eliminate duplicates, so you're writing in SQL, select distinct. So why would sorting work for duplicate elimination? So you have a table, unsorted, and there are multiple attributes, multiple columns, right? And tuples, and it's not sorted. So how do you now, if you want to eliminate duplicates, do this? Well, the obvious reason, the obvious answer here now on the slide is you sorting, right? Why does sorting help? So if you're sorting and you have a duplicate, let's say you have entry like 2, 4, and 7, and 2, 4, and 7 comes here again, and there's some between 8, 9, and 10, or 8, 9, and I don't know, 5. And if you're sorting these tuples based on the attributes, all attributes in this case, or only the ones that you mention here, doesn't matter. If you're sorting, then these two, of course, because you're sorting, will be placed next to each other. And then you can just go down the table, down your sorted result, and see immediately when neighboring tuples have the same value, and then you can eliminate them, right? That's an easy way to eliminate duplicates. When else do you need sorting? Well, a user wants to have sorted answers, right? So ordered by, I don't know, some attributes, you need to have sorting. This is also one case a database needs to sort. Another, maybe not so obvious case is bulk loading. Let's say you have 1 million or several million of tuples, and someone comes and gives you these data, and you want to put them into the database. Okay, you put them in a table, but now you want to create a B+ tree over that. If you have 1 million or several million or even thousands of or 10,000s of tuples, and you want to insert them into a B+ tree, if you have a tree which is empty initially, and you're always calling insert, 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 and so on. Of course, this works somehow. The tree will grow. At some point, these tuples will be inside the tree or indexed by the tree. But it's much more efficient if you're sorting the data up front, if you have a lot of data. And then there are bulk loading techniques for B+ trees and other index structures, which take the sorted input and then construct the tree much more efficiently. In the undergraduate course, we have seen how bulk loading works for B+ trees, but there's also bulk loading for other trees, right? Again, why do I mention this? Well, bulk loading only works if the data is sorted, and external sort is the way to sort large amounts of data if you don't have enough available memory.